Okay, so in this video, I want to talk about the mean value theorem. And instead of just jumping into like exactly what it is and like all the math details, I want to kind of zoom out and do sort of a big picture point of view thing first. So what I want to do before we do anything else, I want to say what is the mean value theorem? But more importantly, I want to talk about why do we care? Like who cares about the mean value theorem? So why is it useful? And I'm going to try to really focus in on that. And I want to answer two things with it. I'm going to do two examples. So one example, one usefulness of the mean value theorem is proving relationships about functions and their derivatives. So how does the information about a function and its derivative, how do those things flow together? And that's really what the mean value theorem is going to be about. So that's going to be one example. And then I'm also going to do something else for fun, which is I'm going to use the mean value theorem to estimate the value of pi. So you guys all grew up with pi equals 3.14159 dot dot dot. How do you calculate that? Like how do you get that mathematically? And the mean value theorem is one way. So that's what I'm going to do. So to warm us up though, like to get us on the same page, I have a warm up problem here. And I have two definitions. So I have, what does it mean for a function to be strictly increasing? And strictly increasing means if you have two values, x values a and b, then f of a has to be less than f of b whenever a is less than b. So sometimes people call this monotone increasing or always increasing. I'm going to call it strictly increasing. So for every a and b with a less than b, we have f of a less than f of b. That's what it means. The other definition is strictly positive derivative. That one's pretty straightforward. At every single point, f prime of c greater than 0. Strictly positive derivative. And the question is, what is the relationship between strictly increasing and strictly positive derivative? And there are two possible things that jump to mind. So which of these two statements is true? Is it true that if you're strictly increasing, then you have a strictly positive derivative? That's statement one. Is that true? And statement two is, if you have a strictly positive derivative, then you are strictly increasing. And what you should do is you should pause the video and think about these, think about them carefully. Which one is true? Which one is false? Are they both true? Are they both false? And if you can answer the question, which one is true, you should try to go further and say, why is it true? So pause the video for a second, write this down, think of some examples of f's that you've seen before, and try to figure out which one is true and which one is false. Okay, so hopefully you've thought about it. I'm going to spoil the answers now, so if you've thought about it, good. Okay, which one's true, which one's false? Answers. Statement one, if it's strictly increasing, then does it have a strictly positive derivative? The answer to that is no. So a lot of people think that this is true, that if you're strictly increasing, then you have a positive derivative. But this is not true. It could be that the derivative is equal to 0. And that happens, for example, in the function x cubed. So the function x cubed is always going up. If you draw a graph of it, it's this funny like wiggle that goes up. It's always strictly increasing, but the derivative is equal to 0 at x equals 0. So it has a horizontal tangent at x equals 0. The derivative is 0 there. So it is strictly increasing, but it does not have a strictly positive derivative. That's statement one. A lot of people have a misconception about that. What about statement two? So it turns out statement two is true. Statement true is a true statement. If somebody on the street asks you, why is statement two true? Why is it true that a strictly positive derivative implies that the function is strictly increasing? I think it's not so easy. And it's easy to think of like weird functions like x cubed. Like it's kind of a difficult thing to figure out. And I think the only way I know how to prove this is to use the mean value theorem. And the mean value theorem is a tool. And I think what it does is it lets you import information from the derivative into the function. So let me tell you what I mean by that. So to talk about this connection between the function and its derivative, I'm going to go back to something we did right when we did the definition of the derivative, which are average and instantaneous rates of change. So the average rate of change, you remember, is this thing on an interval a to b, f of b minus f of a divided by b minus a. This is also the slope of the secant line between a and b. So the slope of the secant line, not the tangent line, the secant line between 2 points a and b. And this is really telling you how is f changing on some fixed interval. That's the average rate of change. The next thing we had was the instantaneous rate of change, which we got from limits and was a long story with the tangent line and limits and doing a bunch of things. And this is at a single point c. So one of them happens on an interval a to b and is really telling you about how the function is changing. And the other one is at a single point, also has something to do with how the function is changing, and is related to the derivative. And really the fundamental question of calculus is, how are these two things related to each other? Because they're related in some way, but what exactly is the relationship? So the two examples I gave before, strictly increasing and strictly positive derivative, they were both facts about this thing. So strictly increasing is the same as saying the average rate of change is always positive, and strictly positive derivative is the same as saying the instantaneous rate of change is always positive. So what we did before, that can totally be reframed in terms of these rates of change. So these are the two things. We got average rates of change, we got instantaneous rates of change. How are they related? And one direction we did in a lot of detail, which is from the limit definition of the derivative. The limit definition of the derivative says that if you know the average rate of change and you do the limit of that, that is the definition of the instantaneous rate of change. So to get from the average rate of change to the instantaneous rate of change, this side of the equation of connecting these two things, that is the limit definition of the derivative. What about going the other way? How can you go from knowing something about the instantaneous rate of change to knowing the average rate of change? The only way to do this is the mean value theorem. And that is why the mean value theorem, that's why you need it to prove things like if you know something about the derivative, then it means something about the function. So if you know the derivative is always strictly positive, how do you know anything about the function? The answer is the mean value theorem. So let me tell you exactly what it says. This is where it fits into the logical chain of things. The mean value theorem is the only tool that for moving information from the instantaneous rate of change, moving it over to having information about the average rate of change. So what does the mean value theorem say? It's very simple in terms of rates of change. So you pick an interval a to b. You have a function f that satisfies the terms and conditions. I'll tell you what those are in a second. But once you have those two things, the mean value theorem says that there is somewhere in the interval ab, so you have your interval ab, somewhere in the interval ab, there is a point c where the average rate of change on a to b equals the instantaneous rate of change at that particular point. And the mean value theorem doesn't tell you where the point is. It just tells you there is some point x somewhere in the interval a to b where this happens. So no matter what interval you pick, there's some point x inside the interval such that the average rate of change on the whole interval equals the instantaneous rate of change at that particular point. Okay, there's some terms and conditions. What are the terms and conditions? F has to be differentiable everywhere, and it has to be continuous at both endpoints. But if you have those terms and conditions, it's always true. And what this does is it's an equality. It lets you turn facts about instantaneous rates of change, facts about the derivative, into facts about the average rate of change. That's why it's so useful. So here's the remark. Where is the point x? The mean value theorem does not tell you where it is. It could be anywhere in the interval a to b. The mean value theorem just says it's somewhere, but nothing else. So it's a bit like the intermediate value theorem we did earlier. Okay, and these are the two applications I want to show you. One is the fact we just did. If f has a strictly positive derivative, then f is strictly increasing. That's one application. And then I'm also going to estimate pi. So I'm going to pause this, and we're going to get the OneNote out, and we're going to do some Blackboard work. Okay, we're back at this Blackboard. Now we're going to do some proofs. So what are we going to prove? We're going to prove the statement that I showed earlier. So if f of x has a strictly positive derivative, then f of x is strictly increasing. That's the statement I'm going to prove. And the if part of the statement, the hypothesis, if f has a strictly positive derivative, what does that mean? i.e. f prime of c greater than 0 for all c. That's what it means to have a strictly positive derivative. F of x is strictly increasing. What does that mean? i.e. for all a less than b, f of a is less than f of b. So having a strictly positive derivative only cares about a single point. That's like the instantaneous rate of change. But being strictly increasing, that cares about every possible interval a to b. So this is something happening on intervals a to b. And that is why it's not a trivial problem. We have to reconcile this difference of instantaneous rate of change with average rate of change. Okay, but here's the proof. So what I'm going to do is I'm going to start with what I want to show. I want to show if a is less than b, then f of a is less than f of b. That's what I want to show. I'm going to rearrange it a little bit because I know that average and instantaneous rates of change appear. So what I'm going to do is I'm just going to rearrange what I want to make it look like an average rate of change. So this is the same as saying, f of b minus f of a divided by b minus a is bigger than 0. You see, because if b minus a is less than b, then b minus a is a positive number. So this happens, it's exactly the same as saying that this is bigger. So this is saying that the average rate of change is always positive. Average rate of change is always positive. Okay, and we want this to work for every possible value of a and b. So for all a less than b, this is true. Okay, so here we go. Here's the proof. F of b minus f of a divided by b minus a. That's an average rate of change. So this is an average rate of change. So by the mean value theorem, this is equal to f prime of c for some c in the interval AB. Okay, so maybe this is where we need to take it back up. If f has a strictly positive derivative, maybe we should also add a little asterisk here, and satisfies the terms and conditions of the mean value theorem. And many functions will. So for example, if it's defined everywhere, if the derivative is defined everywhere, that's okay. So we are using the mean value theorem, so we better make sure that it's okay to apply. But as long as it does, f of b minus f of a divided by b minus a equals f prime of c for some value of c. That's the mean value theorem. This is by the mean value theorem. And we were told that f prime of c is always bigger than 0, no matter what, which is greater than 0. And so this line is, since f prime of c greater than 0 is always true. That's it. That's the proof. So what did we do in this proof? We converted what we wanted to show. We converted that into something about average rates of change. And then we converted average rates of change on this side of the equation, the average rate of change. We converted that into something about the instantaneous rate of change, f prime of c. And we know something about the instantaneous rate of change that was given to us in the problem, if f has a strictly positive derivative. So the mean value theorem is this bridge that converts average rates of change into instantaneous rates of change, and sometimes you know something about those. So let's finish it off. Because f of b minus f of a divided by b minus a is greater than 0 for all a less than b, therefore f of b is greater than f of a for all a less than b, therefore f is strictly increasing, which is what we wanted to show. Okay, so that was using the mean value theorem to prove something about the relationship between functions and their derivatives. If the derivative is always strictly positive, then the function is always strictly increasing. Okay, that's that one. That was example 1. Example 2, I'm going to estimate pi. So you guys know that pi equals 3.14159. But how did mathematicians come up with that? And that's what I'm going to do. So I'm going to pause the video here. I'm going to get something out on Desmos so we can start talking about this. But then I'm going to use the mean value theorem to estimate pi.